Hi everyone, welcome back to the Hive development log. In the last video I noticed that my volume on my microphone was set to 0, so I'm surprised that you could hear anything at all. I suspect you probably couldn't, so we might recover that in this development log. I might actually go and delete the other one, which makes more sense. So assuming that we haven't seen the last video, a quick recap. Since we did our last development log, I've worked on quite a lot of things behind the scenes, and one of those things has been supporting hive binding, which was somewhat difficult to do beforehand. In fact, you really had to do it using code. So you'll notice that in the game logic panel, there's a new panel called Hive Logic, and that has a node tree drop-down menu, and you can select a node tree. Now I've created a node tree called cubes to demonstrate some new features we've added to the editors. As I've already explained, I think once at least, Hive has the ability to output an intermediate format called a hive map, and if I open the cube hive map, you'll see that we have basically some information describing the connections and the workers themselves. And these basically derive the UI, so you need these in the editors in order for the UI to work. If you delete a node tree from the UI, you'll notice that it still is there because you have to actually remove the users. If you hold Shift and click the X, then that basically deletes it from the node tree window, and that in turn deletes it from the text window. And you'll notice we now don't have a text file here. You can load worker maps into the node tree UI by either opening it in the text editor, saving the file and closing it and then reopening it, or if you want to save time, do the same, but instead of closing the file, click Synchronize in the Hive options. But to do that you need to have Use Hive Logic enabled, and that'll basically save the current UI system, load everything back from the Hive maps, and that will include the new Hive maps you've added. So that's important. So if we add a new hive map, node tree, we're going to call it cube just to make things simple, and we're going to select our cube, and we're going to click node tree and select the cube node tree. And now our node tree is set to cube, and we can actually look at it here as well. So what we're going to do is we're going to add Sparta triggers, Sparta's sensors near. And now we're going to change this to just normal Sparta level. I was in advanced Sparta, and you'll notice that we only have 3 important connections here. And I'm going to quickly fold these values in so the pins are gone, and I'm going to set the distance on the near sensor to 10, and the filter value will leave. I haven't implemented that yet, but you can filter by the ID, by the property, or by the material. To explain what that means, you can look for a certain material, a certain property, or a certain game object name, which is basically what ID corresponds to. But for now we don't implement that, so we leave that folded and empty. Now I'm going to add a Sparta trigger, and it's an if trigger. And I've already told you what these do, but they basically poll the near sensor every frame to work out if it's active or not. And now we're going to add an actuator. We're going to set it to mod property, and the reason we're setting it to mod property and not set property is that I haven't fixed set property yet, so we're going to use mod property to make sure that it works. Don't worry about the modification mode as long as it's add, or in fact let's leave it at add. That's the only one that will really do what we want it to do. And we're going to add a property to our cube called prop, set it to int, and click the debug value. And we're going to remove the debug value from the cube hive map property as well, which is here. This is created by the Hive Logic editor. And now we're going to go to our mod property worker, fold in all the values so that we can edit them in here more easily. We could expand them and edit the nodes themselves, but that's a waste of time. So we're going to change the worker type to integer, click create instance, and make sure that it's still bound. And then we're going to change the modification value to 1 and the property name to prop. And basically what this means is that every time we get near an object within 10 units, we will basically increment the property value on this cube by 1. And that's every frame. So now if we add a cube, grab it up on the z-axis and enable physics, so it falls towards our target and the debug properties are enabled, you'll see it falls and then the property starts increasing when it gets near. to show you again, it's here, and it increases when we get near. Now, that's good. And we can even make this show that it works for more than one. We're going to grab this cube up on the z-axis and then grab it to the x so it doesn't collide. And you'll notice that immediately that one counts, and then the other one counts. And if we can grab it up just enough, hopefully one will count and the other will stop. There we go. And it does what it's supposed to do, which is good. So the important thing to take from this is that we've now implemented most of the Sparta nodes. I've done this video before because I realised the microphone volume was off, so I may be repeating myself here, but essentially in the Sparta library we have debug print enabled, which doesn't really do anything that you wanted to do, but it's useful for me. We have mod property, parent and set property implemented. Stop won't be difficult to implement. Resume and pause will be more tricky to implement. Object shouldn't be too tricky. Motion is a little bit more tricky because it requires some thought about how we organise things, just to ensure that it's extensible in the future. Message shouldn't be too tricky. Launch, a similar one to object, and kill, again, the same thing. So the actuators are probably the most tricky thing to do. Most of the accessors work. Some of the advanced Python ones still need to be implemented. All of the all of the processors, I think, work. Perhaps the Python one doesn't. All of the triggers work, and all of the rerouters work. So to demonstrate this with a rerouter, let's add Sparta rerouter hop in, and we'll connect it to the near sensor, and then we're going to add a Sparta rerouter hop out, and connect it over here, but first delete the connection that was there. And now it's wireless, if you like. And we don't need to put a name in, because if we don't, it'll choose an empty string and it'll still work. So just to demonstrate, we start the game engine, and the properties count. So that's the main thing. Another thing that you can do with rerouters is if you add a splitter, then you can split one output into multiple outputs just for ease of use. So my plans from this point forward, I don't know if I've said this already, I don't think I have, are essentially in fact this is the useful point. Before we move on to those plans, it's important to look at how the near sensor has been implemented. In Blender, the logic bricks get away with more than they should, meaning that that's not directly true, but they have access to more information than Python does. Logic bricks can create physics objects and they can destroy them, and so the way in which we implement near sensors in the logic brick system is we essentially create a collision object, which is a sphere, and we parent it to the game object and set it to the correct radius. We can't do that in Python, but Panda 3D can. The options to solve this are either to add a very limited Python API just for adding collision objects and setting the sizes, which would be very limited and probably useless apart from in sensors. It'd be much easier to implement, but probably quite useless. The other alternative is to actually implement a full Python API for Bullet, which would be a lot of work, but would give you full control over the Python objects. But it's a lot of work, and I don't think there are many developers who think that's going to be a worthwhile spend of their time, given the other issues that face the Blender game engine. But that is not for this video. The third option is to not use physics objects, which is what I've gone for now. And if I do start using Panda 3D, then I will implement it properly using physics objects. The way we do this at the moment is quite interesting. Essentially, we compare object centers. So I have a special drone, which is essentially a big black box that handles all of the complex logic, and all it does is it has some plugins, and these plugins and sockets as well, and these plugins and sockets basically interface with other things. They're almost like direct connections to other functions that are exposed by other big black boxes, and some of those functions enable you to do things like get the matrix of an object, get the names of all the objects in the scene, and I've also defined some plugins which are things that other objects can use, other big black boxes, and that is a collision test, sorry, contact test, and also create node. And these are fake, these are stubs, and all they do is they pretend that we have a collision API. So when I move to Panda, I can implement this drone again without having to change what's in the worker, because the worker uses those plugins, and the worker basically asks, can I do a contact test, and also can I create a node? So when we do get a proper physics API, either in Blender or in Panda, I shouldn't need to change its worker. It already does what it's supposed to do, and I just change what information I give it using a different drone. But the point is that every single frame, the near drone will look at all the objects in the scene and create a KD tree from their positions, which is basically an organized spatial structure. And then every time we run a collision test from the worker, we look at the KD tree which we've already built and do a ranged search. And then we basically create some contacts from all the hit objects and make it look like a hit contact result from the Bullet physics engine. And then we add that to the contacts list. So the important message to take from that, if you haven't already, is that it's fake, which is not a real problem for most users actually. Most of the time you won't notice it. But what it means is that you need to include the margin of the object that you would normally have as the detection distance. For example, if we look at this scene, we have here a cube and another cube, and because we're detecting centers, those centers are a little bit further away. You can see the centers are further away than the borders of the objects. So the borders of the objects are literally here and here. So this object would detect this bottom object more easily because it's closer if you look at the physics mesh. But because these are further away, when we check the centers, we need to add a little bit more distance to our sensors. However, this isn't the only option for using near sensors. The other option, which is quite easy, is essentially create a child object and parent a collision sensor to that, which are nearly implemented. I'm working on those. And then that can act as your very own sensor object, provided that you enable the physics type as sensor. If I can escape out of this, yes, you just change the physics type to sensor and then you can do it. So it really just requires a workflow difference, which is good. And as a point of information to enable communication between the two hives, you would then use a message worker to do that. So the message would go between the child and the parent. At this point, I really feel that once I get all of the actuators implemented and most of the other components and sort of polish up the rest of the system, it'll become much, much easier to use because there's the actual functionality there that you want, rather than having to approximate it in every single corner. And from there on, it's basically bug fixing. So thank you for listening, and I will keep you posted.